start recording and stop talking about the good old days. Okay, so homework 10 was due today. 2 more homeworks due. We'll have the lab 4 quiz on Friday. The last pre-lecture is next week, and homework 12 is due next week. No lab on the 23rd, and our final exam is Wednesday, April 28th from 3 to 5 p.m. unless you are exempt from the final. Okay, we have rules for that now. Some grade increasing opportunities. Yeah, it must be spelled wrong. Opportunities. The course evaluation is worth 5 extra credit points on the final exam, and also required if you're exempt from the final. The practice final, which I should get posted tomorrow, is worth 10 points on the final exam. And homework 11 is worth 25 bonus points. There's 25 bonus points on there, so it's like 125 out of 100. And there's 5 homework points on bonus on homework 12. I will take 1 week worth of late lab accepted to my email by 4/23, last day of class. Okay, so get that in, and that will take away one of your lab grades you didn't do so well on. That's 1 week of lab, so you can't like turn in lab 4. That would only count for 60 points maximum. Okay. My author's here, and I don't know who it is. Okay, I'll figure that out later. Okay, so what we've got going on here is the final exam exemption. You have to have an 88% or greater overall average. You will get an A in the class. You must turn in a completed lab 4 to be exempt, and you must complete the course evaluation. So that should get about 1/3 of the class out of here. Good thing for the rest of you, I'm not grading their exams with yours, and these are the people who generally have a higher exam grade. So if I'm looking at adding points to your final exam because the average is too low, you just got the curve busters out of here. Okay, electives for the fall. 490 is on the books, but apparently students can't enroll in it. I sent an email to Brian and he hasn't responded to me. So I will send, if I don't hear from him by tomorrow, I will send emails out to more people. Oh, you can enroll. Yes. Okay. So he fixed it. You can enroll in 490 for the fall, 32 seats. I'm telling you guys first. I'll tell my 280 kids tomorrow. It is hands-on. We usually use the lab equipment in here. Learn to use the oscilloscopes and the function generators, and we learn to use the DC supplies. We do a lot of analog measurements. We actually do the printed circuit board design for a simple circuit, very simple circuit. It's nothing fancy. We don't actually go out and get it fabbed, but I just look at it and make sure it's right. We do some soldering, build a simple printed circuit board. We look at a lot of sensors and what the analog considerations are. I spend a whole day talking about ground. Where else can you get this in electrical engineering? And ground is important and way more complicated than any of you think. There's these horrible things called ground loops and divided grounds. Why do people have analog ground and digital ground? And how do you connect them together and why? So all the great mysteries that you need to actually build electrical circuits that work are what I tried to get into that class. Okay, good. Now I get to work on memories in the spring. We'll start that campaign in a few weeks. What? Yes. Email kyle.winfrey@nau.edu.
I think realistically you should just start
Okay, so this is data converters. Yeah, today in memories, it's kind of weird. We start the last week of class is CMOS imagers, and this is what I spent my whole life working on. So there was like Dr. Brower's synopsis history of it, and I'm looking at it and going, no, that's completely wrong. That's not how it happened here. And so I just start writing these slides, rattling off names. So this guy did this, and this guy did this, and yeah, and I knew them. So ADCs and DACs, my big experience with them was, okay, a couple of things. At Kitt Peak, we had to have really high speed, high resolution ADC converters. We had an analog signal chain that had 35 electrons of read noise, referred back to the input. And we had to read it out fast because we're reading out 1 million pixels before all the data goes bad, right? So we had these really precise high-speed converters. My job was to test them. We had to, Al picked one out. Of course, he didn't believe the data sheet. Good reasons. He wanted to make sure it would work for our application. So me and the PhD from Bell Labs tested ADCs and wrote a paper on it. We came up with our own algorithm for it. I didn't learn about ADCs and DACs when I was in college. They didn't really exist when I was an undergrad. And when I was a grad student, I was doing device physics. I was deep into the CMOS. So a lot of this stuff, really, when I learned it, it was just me sitting there going, okay, how does this work with a calculator in my hand, just punching numbers in. And I didn't know there were actual formulas for this until I started doing it. I did not look at the book, but the slides made enough sense to me. I could do that. So we're going to have an introduction. We are going to talk about some digital to analog converters and look at ways people build them. We did that inside integrated circuits. We did that at JPL. We built some 5-bit DACs. They didn't have to be super precise. They didn't have to be super. We didn't have to get the value we wanted really that closely to the input on the output. We didn't have to nail it. We just needed an output that was stable. And we would be happy for that. For basically biasing up our CMOS imagers. We also built a 10-bit A to D converter. It was a really cute design. We had the first array that we did this on had 512 rows and 512 columns, and we wanted to get the data out as fast as we could. So we had 512 ADCs in parallel, one for each column. And we'd read out a row and get all the columns from that row simultaneously. So the device had to fit in a 30, at that time it was a 30 micrometer pitch. So it was 30 micrometers wide and about 1 centimeter long. And so I did a little bit of work on that too. So we'll look at the different topologies, and then we'll look at some basic, really basic performance characteristics of ADCs and DACs. We'll go more deeper into more stuff like if you're using an ADC for a signal chain, how fast do you need it to run, what kind of input noise you need on it, how to pick out an ADC or DAC. And you will have literally thousands of choices. Most of the information I got is I found a tutorial on TI. A lot of the manufacturers they want people to use their stuff. So they will tell you, okay, you step by step, this is how you get started. So a lot of information on the manufacturer's websites. That's the performance limitations part of this. So we've got 3 days for this. Wow, this is a luxury. We'll see. I may start the final review early. So in the real world, information is continuous. You've got some kind of IoT system, or you've got some kind of sensor on a car that you're trying to get it to, more automate the driving algorithms. You've got these sensors. They're taking in data from the real world. It's continuous. It's variations in atmospheric pressure, variations in the direction the sensor's going, variations in temperature. They don't change in discrete steps. So they're analog. And you're going to have to, generally these sensors tend to be high impedance sensors, which means they can't drive a lot of current. So if I run them into a ADC on a microcontroller, typically it's enough to kind of like just take and saturate the sensor so that you don't get any data out of it. A lot of times you need an analog front end for that. That's what we talk about in EE380 in the fall. So we got the real world here, or some kind of analog of it. Some kind of pseudo real world there. We've got some kind of sensor here. And this sensor is going to be driving an ADC. So it needs an analog front end in there too. And the details and the block diagrams, all that's reserved for 490 in the fall. So this ADC, which is a class I completely wrote, with any input from Dr. Brower whatsoever. So you get raw, unprocessed me. I'm going to take this, and then the DSP guys are going to have a processor, and they're going to look at the analog data stream coming in, and they're going to perform, the analog data stream is going to be in a stream of digital numbers. So they're going to look at those digital numbers, perform some kind of algorithm on it, a Fourier transform or a whatever the DSP guys do, multiply it by something, divide it by something, add a constant to it, filter it in whatever way they want to do it, and they send it out in the form of a digital number. So this digital number, before it can act on the real world, is going to need to change into an analog voltage that you can use to for an actuator. An actuator is just a fancy name for things like motors, light bulbs, microphones, speakers, things that are going to be actually send data back out to the real world. So I've got a sensor. My sensor is a microphone. I'm taking the microphone sensor, putting a good analog front end on it. I have got to add that in, running it into an ADC. The ADC streams that data to the processor. They maybe filter out noise and pops and some high frequency stuff that you don't want to hear. Run it into a DAC, which actually produces the analog voltages that cause your big boom speakers to go back off. Everything's an audio system to me. Okay. So these digital signals, and thank goodness for once in our lives, our minds matched up. I think Big Indian is the only way. I think there's been a long-going dispute in the lab for the last 4 years. Some people do their data Little Indian. I've told them they were wrong, and then I told them I don't care. Just pick a direction and make it standard. And it started again. And so my only thing that I'm going to do after that is I'm going to declare a compromise, and we're going to use Middle Indian just to confuse everybody. But Big Indian, the most significant bit comes first, just like you're writing a number, 5,762,000. 5 is the most significant bit. It comes first. This is the language that we're going to use, and we're not changing that ever. And fortunately, I would have had to rewrite the slides because I would have just made me mad. So I have some binary word. It's a stream of binary digits, zeros or ones. No trits in this class. N is the number of bits, so it's the number of digits I have in the string. The most significant bit is B1 because it comes first, and the least significant bit would be Bn because it comes last. Now, if we want to represent this digital signal as a portion of the full scale, what we could do here is we could take the value of each bit and divide it by something that represents the weight of the bit. So the most significant bit we divide by 2 to the first. So it's like half full scale. If that one's set, I have half full scale. Then I take the value of B2, 0 or 1, and divide it by 2 squared, 4. The next one gets divided by 8. all the way out to the least significant bit, which is divided by 2 to the number of bits, 2 to the n. And this will give me, if I add all this up, I get the decimal equivalent of this binary number. So we could have taken from 110, we could have taken that binary number and found a decimal equivalent for it. We're doing the same thing here. We find the decimal equivalent for that and divide it by 2 to the n. We will get that fraction of full scale that that number represents. So I get a number here. It's a 4-bit number. We always put the zeros in the front. And this is a decimal equivalent of 5. I already said that. I did that automatically. N is the number of bits. And there's 4 little bits there, so it is 4. F, the fraction of full scale, would be 5 over 2 to the 4th, which is 16, 5/16. I can do 8, so I can't do 16ths. 0.315. That sounds rightish. 0.315. So I would expect that to represent, we're about 3/10 of the way up to full scale. Now, if I have more bits, it gets a little bit more complicated. So here I've got this one right here. We'll go through my 210 algorithm, 110 algorithm. There is no 210. My 110 algorithm here. This is the 2's place. So it would be 2 to the 1st. This is the 2nds, the 3rds, the 4th. So I need a plus 2 to the 4th. The next one has a 1, so plus 2 to the 5th. 2 to the 5th. How many ones do I have here? I have 1, 2, 3, 4. Okay, great. So I've got 2 to the 6th, and I've got 2 to the 7th. And if I take those and I punch them into my calculator and I add them all up, I can get the decimal equivalent of this. Now, an amazing thing with most modern calculators is you can do binary to decimal conversions on them. Use your tools or engineers. That's what we do. Oh, yeah, that's okay, 0.3125, you're right. Now, usually I use 3 significant digits. When I start doing analog to digital converters, I start going out to as many digits as there are, because a lot of times when you start adding those up a million times, losing that last couple of digits makes a big difference. So I use more significant digits when I'm dealing with ADCs, and that would be wait, that is 121 in decimal. So if I wanted to figure out how many bits do I have 1, 2, 3, 4. I have 8 bits. I've got a byte. So if I wanted to figure out my fraction of full scale, it would be 121 over 2 to the 8th, which is, I can do this with, no, I can do this without counting my fingers now. It's a new trick. 256. Of course, it's my office number. It's a byte. Okay. I was using my new memories trick. Never mind. 0.473. In memories, I used to, my first year teaching it, I actually walked around with a little chart that said 2 to the 12th equals 2 to the 24th equals all the way up to a terabyte. So I could just look at that, and then I realized I suddenly, I don't know, daylight hit me. I figured out the pattern. Okay, so that's 0.473, and that was what we were looking for. So about halfway full scale. So the least significant bit, when we're dealing with a converter, the number of bits is going to tell me, the number of bits in the voltage range on the input tells me how many volts each one of my LSBs count. So we got to learn how to calculate that too. 1 LSB, to get the value of that, is going to be 1 part in 2 to the n. Now, the voltage range of the analog signal is usually defined by the VREF on the converter. Or if you're using the crappy Arduino converter, it's like 5 volts and you have no choice. So that's the full scale there. It's either the reference voltage or it's the one that the part tells you it is. Divided by 2 to the n would give me the voltage value associated with that least significant bit. I've never ever seen an ADC with a gain other than 1. So let's not talk about that. You don't want to put gain in the ADC because you want to put the gain in the front end in the analog signal chain where you have more control over it. You can get what you want. So the LSB and the VLSB, if I only have a 3-bit converter, the smallest number of bits I've ever seen anybody do is 5, and that was on that little one we put in the biddy. Into the 3, so we want to find out what fraction is the LSB and how many volts it represents. So the LSB would be 1 over 2 to the 3rd. So that's I wrote the answer down instead of writing what I was saying. It would be 1 over 2 to the 3rd, which is 1/8, which is 0.125. And the amount of voltage that one change of 1 LSB would represent would be 8 times that, because I have an 8-volt full scale range, so that would be 1 volt. VLSB would be 1 volt. And let's just skip ahead. Okay, so let's, because I don't want to do this over and over again. If I have 12 bits, now there's plenty of 12-bit converters on the market. Each LSB would be 1 over 2 to the 12th fraction of the full scale input range. And that comes out to be, I didn't even bother to calculate that. The voltage of the LSB would be, with a 1.6 volt reference voltage on my converter, would be 1.6 over 2 to the 12th. And that comes out to be 390.625 microvolts. And I use all of my significant digits in this case, yes.
If you wanted to find the MSB, then would you just have to multiply the full scale voltage by 2 to the n minus 1?
No, okay, so the MSB for that converter would be half of the full scale.
Oh. Okay.
And the next most significant bit, like the next to least significant bit would be 1 over 2 to the 11th times the voltage.
Oh.
Okay. Things I tested on, yeah. That was like a 3-month project, test the ADC. Oh, we were talking about Fowler in the last class today, so never mind. I won't give you any Fowlerisms. This is a digital to analog converter. So I'm given, what I'm doing is my input is a digital number. My full scale voltage, and I can determine what the output, what analog output I would see for an ideal converter. No converters are ideal. So this one, if I look at this, this is the decimal equivalent of this number is 5. 2 to the 4th is 16. So I'd have 5/16 times my full scale voltage, 3 volts. What I would see on the output if I've correctly programmed this device and put in the 3 volts was stable and all that good stuff is going on, everything's working correctly, I would see 0.9375 volts on the output, depending on how good my meter was. You're using your meter, yeah. If I go up to a larger number of bits, so this is 8, 2 to the 8th, I'll just tell you right now, I see 4C. If I want to find what voltage this would represent, it would be 5.12 volts would be my full scale, times The decimal equivalent of this is 217. So times 217 over how many parts I could possibly divide that in, which would be 2 to the 8th. So I would be expecting to read 4.34 volts on my output. Okay. Basic calculations with these little gizmos. Of course, there's offset errors, there's gain errors, there's all kinds of errors in them.
So 5.12 times 217.
Yes.
And where does the 217? I see it's from the.
It's the decimal equivalent of the binary number I was given. Yeah.
That's 2 to the 8th.
Yes, that is 2 to the 8th. Okay. Yeah, this is where I feel like you guys have made it through 380 and I can start talking to you. It only takes me like 2 years of doing this before I can talk to you. Okay. Now I've got my 3-bit, my mythical 3-bit DAC that we're going to use a lot in this class just because it's easier to draw the schematics and do all kinds of good stuff with that. If I put a digital code on the input of 000, I'm expecting, and my full scale voltage is 8 volts. I'm expecting my output to be 0 volts. That is a 0. I started to write 1. 0 volts. If I put a 001, 1/8 of full scale would be 1. And this would just keep on going down. 2, 3. The digital equivalent of the code I get in would be what I get on the output. The most voltage I can get out of it is not full scale. It's 2 to the n minus 1 over 2 to the n times full scale. So for a 3-bit DAC, I can only get 7 volts out of it because I can't go to 8 with 3 bits. I can only go to 7. That's the way they work. That's the way the universe conspired to make them work when people were first starting to design these things. You can't get full scale voltage out of it. You can get close to full scale. A lot of times an LSB is only like microvolts, so people don't know the difference. If I drop the full scale voltage to 1 volt, what I'm going to do here is everything gets divided by 8. So I have to count in 8s, 0.125, 0.25, 0.375, 0.5, 0.625, 0.75, 0.875, and I'm done. So I can get closer to full scale in that case, as far as the numbers go, but it's still pretty small. If I get more bits, I can get closer to full scale also. So if we want to draw a picture of this, we want to draw a graph of what a DAC does. I put in a digital code. I put in a digital code of 0, I get 0 out. If I put in a digital code of 1, I'm just going to write this as 1, I'm going to get 1/8 of full scale out. I cannot put in any numbers between 0 and 1. There are no decimal points in binary except in 110, where I just use it to torture the students. I make them do a couple of calculations in decimal binary with numbers. I gotta put something hard in that class. 2 is gonna go up, 3 is gonna go up. This is gonna follow a straight line, but I can only put discrete values on the input, so I really only get points, and the points are not connected on the output. I'm going to get discrete values of voltage on the output based upon what values I put on the input. The value of VLSB is this voltage right here. How much does it change for every step up? As I count the steps up, I'm going to get 1/8 the full scale, always, with a 3-bit DAC. If it's 4 volts for a 3-bit converter, I'd have a 1/2 volt step size. And then here's the graph actually drawn more neatly. And this works for any 3-bit converter. This is the digital code I put in on the input axis. On the output axis, I have the voltage of the one out that I get. And for an ideal DAC, it always works like that. We'll talk about non-ideal later. Non-ideal is usually something you can kind of mathematically model. And in the real world, it's much harder to do that, so you just measure it and use statistics. Why statistics is more important than you can imagine. Okay, so when we talk about these performance criteria, this is some of the more basic stuff we can talk about. The number of bits. You're going to get a higher resolution if I have a higher number of bits. So from a performance standpoint, number of bits, higher number of bits is always better. But then there's problems. As I increase the number of bits, the cost of the device goes up, its physical size goes up, the amount of power it dissipates goes up, and how fussy of an analog designer I need designing the analog chain who is driving this ADC, he gets a lot more expensive too, or she. So you kind of pick the resolution that matches your application. With the whatchamacallit, how many bits is on? It's an 8-bit DAC on the Arduino, isn't it? Okay, I think the DACs and the ADCs on the Arduino are all like 8 bits. Yeah. So it's a fairly low resolution, but it's cheap to build. It's easy to fit inside a microprocessor, and it gives most people enough resolution for their application. If you're talking about a 5-volt signal, like with the Arduino, over 2 to the 8, that's 256 parts. It's about 20. I'm getting about 20, I think it's about 20 millivolts per step. And most people can't design an analog chain that's good enough to give you less noise than 20 millivolts per step. You actually need something, you need a professional to do better than that, or semi-professional. So resolution, the best thing to do is pick what you really need for that application. And in 490 in the fall, we go through and we actually look at how there's an algorithm TI's developed for picking that's on one of their tutorials for picking an ADC. It's going through and figuring out, you know, what signal resolution you need, how many numbers of bits, and all that good stuff. So we'll talk about that. This is mostly an introduction. So speed usually represents the time it takes to convert. So you're going to need some time where the analog signal on the input is stable. This is called the sample time, plus the amount of time it takes the converter to convert. Those two together, when you add them together, give you the total time to convert. It's usually written on the data sheet as a clock frequency or a number of samples per second. You always need your speed of the converter. It's like the basic rule of thumb. Nyquist criteria, the Shannon criteria, it needs to be at least twice the highest frequency in your analog signal. So you spec it based upon what analog signal you have. Faster is better, but faster is noisier. And faster is fussier from an analog standpoint. You never spec your converter to go faster than you need it to, because it will set off all kinds of, a fast device will set off all kinds of oscillations in the rest of the system. This is the truth, Dr. Brower. No, there is no one answer. Chip area. Ideally, we want the chip to fit in the smallest space as possible. But to get performance, we're going to have to cause it to grow. And of course, the best thing is it doesn't consume any power whatsoever. but I can't build that. So lower power, and I'll get lower power if I go to a smaller number of bits and a slower converter. So all of these things are trade-offs, and you just have to match it to your system requirements, which makes the first thing you always want to do is figure out what your system's requirements are. Accuracy. Now these are some things, the gain and offset error are pretty easy to correct with like little algorithms inside an Arduino. And you can correct for those, that non-ideality pretty easily. Monotonicity. Yes, I can say that word. It's a real word. And I didn't make it up. It's something you can't correct for. If you ever see a data sheet and it does for an ADC or DAC, and it doesn't say guaranteed monotonic in the first like 4 sentences, don't buy it, because they can cause all kinds of controls problems, and we'll talk about those later, probably in 490 in the fall. I won't get that deep into it here. And then differential nonlinearity. Differential nonlinearity is, we've gone through and done a bunch of calculations, and we said the step size is always 1/8 of an LSB. That would be true if you had a perfect deck. Sometimes it's a little bit less than 1/8, and sometimes it's a little bit more than 1/8. Now what DNL represents is they take the smallest bit size that you actually measure for that DAC, and they take the largest bit size that they measure for that DAC, and they find the deviation from one LSB. And whichever bit has the largest deviation from that one LSB, it specs the differential nonlinearity. It's the maximum difference that you can expect in bit size for any one of them. Integral nonlinearity is the integral of differential nonlinearity. You literally, if you have like, okay, you have one step size that's 0, and the next step size is 1 1/4. You keep a running sum of what each of the step sizes are, and you draw a straight line saying if it was perfect, it looks like this, and the maximum deviation from that is integral nonlinearity. We'll actually do some calculations with that towards the end of this section, probably either tomorrow or Tuesday. It's Tuesday. So we'll talk about those some more. So for an analog to digital converter, philosophically, what we want to do is, we've got an analog input and sorry, I have to stop and before I start talking. Analog input with a digital output. We're going to put a number in here. This is the voltage that I input to the device. And I've got a 3-bit converter with a full scale region like this. We want to figure out, make a prediction as to what number I'm going to get out of that. Well, the way I do that is I take the voltage I measure, I divide by the full scale voltage, and then I multiply it by the total number of, so this is the fraction of the input on this front end, the fraction of Vx, the fraction of full scale, and I multiply by the total number of binary possibilities, and I round that to the nearest whole number because I can't get numbers after the decimal place. So if I want to calculate this and figure out what number I'm expecting on the output, I am going to round the voltage that I put in, 1.65 volts, divided by the full scale voltage, 2 volts, and I am going to multiply that by 2 to the 3rd. So I have 8 possible numbers on the output. And this will give me the decimal equivalent I'm expecting on the output. And I do that calculation, and that comes out to be 6.6. That's in decimal. And I can't get a 6.6, so I'm going to round that up to 7 would be my ideal. So that would be 7 on the output, which is a base 10, which would be 111. And then I could do this repetitively, but I don't see the point in that. Get to do some of these on homework 12. We're already covering homework 12 stuff, so you're ready for homework 11. Now with my ADC, I'm putting in a voltage here. And if I put in any voltage between, and this is 1 LSB, if I'm putting in any voltage less than a half an LSB, I'm going to call that 0. And then if I get a voltage between a half of LSB and 1.5 LSBs, I'm going to call that 1. And so I actually get a voltage transfer curve that looks like a stair step. If V full scale was 4 volts, 4 volts would be right here. And I've got a 3-bit converter, so it would be a half a volt for each one of these. I would expect this to trip at 0.25 volts. VLSB is a half a volt. I just did that in my head. This would go at a quarter. This would go at 0.75 and all the way up. Okay. So the stair step represents, less than half of an LSB or 0, half to 1.5, or that's what I just said. We get that stair step in there. So I got this stair step curve. Now, ideally, what I would really want my converter to do is follow this blue line, which is impossible. This is the V out equals VN line. It has a slope of 1. Now, if I pick a value, let's say pick a value right about here. I could be off as much, my answer could be off as much as a half an LSB. And I can't get rid of that, no matter what I do. It's a fact of life by putting it into the digital world. So what we say is that these ADCs have a minimum quantization error of a half an LSB. It could be dead on perfect. There could be no error between your analog signal and your digital output. Or there could be a positive half an LSB or negative a half an LSB. So they graph that like the, no, I'm sorry. It's the minimum error. It's plus or minus a half an LSB. I was not getting the slides that I was expecting to next, and this is upsetting me. This is what I was expecting to get next. So if you actually plot the error for an ideal device versus input voltage, you get this kind of sawtooth curve where it hits 0, and I'm not frozen. I'm just I learned a magic trick. That was usually when I was upsetting and pushing the buttons. I figured out how to fix that. It only took me a year. There's a little button on the side of this device, and it didn't come with a manual, so I couldn't read it, and I had no idea what it did. But when it locks up, I hit that button, and it just unlocks. Okay, magic. So when I have 0 quantization error, my input voltage increases. I'm still getting the same number out, and then it hits a half. Suddenly, my quantization error is minus a half an LSB, and then it keeps on increasing through there. And that you cannot get rid of. So let's go back to the slide that I was actually supposed to be talking about, was this one right here. So B full scale is 8 volts. We have an analog input of 1.8 volts. We want to figure out what number I'm expecting on the output. So I say, okay, it's that little formula I had. I round. I used to just punch this into the calculator. And when I first learned there were formulas for this drove me crazy. I'd punch it into the calculator and I'd get it wrong until I figured out what the right answer was. Sometimes it would take 2 or 3 iterations. But I round this 1 point in the fraction of the input times the number of possible numbers, and 10, that we've already done a calculation like this. 10, this comes out to be, when I round it, it's 2 decimal. Remember, the answer is going to come out in decimal. So that would be 0, 1, 0 binary, isn't it? What the code I'm expecting on the output. Okay, and we talked about that. You cannot make the quantization error smaller. You can make the voltage, it's always half an LSB. If I want to make the quantization error smaller, I need more bits, or I need a smaller full scale voltage. And you can usually control that with a VREF on your ADC. Never tie VREF to a power supply, like a power supply from an Arduino. You're asking for trouble. It's noisy. You want, they actually sell chips. I might as well just tell you now. People sell chips. They're called voltage references. They're amazing. You put a power supply to them, and whatever voltage it says it puts on the output, 1.5 volts, 1.2 volts, is what it will give you. And it will be dead on, rock steady at that voltage with very little noise. And this is the kind of signal you want going to your reference voltage on the ADC. If you run a power supply from an Arduino that has a whole bunch of noise on it, what you're going to get is you're going to, even if you put a DC input into your ADC, you're going to get a whole bunch of noise on the output. Another reason why the ADCs and DACs on the Arduino are lousy. That and the people who designed them don't understand analog. And I have proof of that. There's an 800-page manual. Never mind. I have seen DACs on Mac. No, was it a DAC or was it an ADC? It was an ADC on a microcontroller, and they were using this in Flickamas lab. And I actually had the kids run a gain transfer curve on it, and it looked like this. It was an ADC, so counts versus VN. And when we measured it, it looked like this. And they had to get the thing out like in the next day because the seals were migrating, and they would have missed the whole thing for another year. So we actually had the kids do this, is write a lookup table. If you get this number of counts, it's this voltage. If you get this number of counts, it's this voltage. They did it with a lookup table, and that's how they fixed that. We have enough computing power to do that now, but it was really bad. Al Fowler would have been screaming. Guy had tantrums. It was like, is he in a Fowler? And he had days when he was almost like bipolar. It's like he's in a really good mood today. He's laughing, he's joking, he's really happy. And then there became the days when he was in a Fowler mood. There was one technician in the lab. The guy wore this big wad of keys on his belt, and a really brilliant guy. And I mean, I wouldn't miss working with him for the world, but you know, you just had to put up with some personal quirks. He had this big keys, and whenever Dan would hear Al's keys rattling, he'd start to sweat because he didn't know what was going to happen next. I could handle it. I've been around enough people in my lifetime who've been slightly, it doesn't bother me. It bounces off me somehow. So the max, okay, I was talking about Al Fowler too much in the last class. He was brilliant, and I was like, had stuff named after him. What is the maximum error for the following cases? So if I have 3 bits and a full scale of 8 volts, my VLSB is going to be 8 divided by 2 to the third, which is 1 volt. So my maximum error is a half an LSB, would be 0.5 volts, would be the error. That could be significant. If I go to something like this, I have a smaller full-scale voltage and I have more bits. My error is going to be half a bit. So, and then BLSB would be 1.6 over 2 to the 12th. And this is number 12. And this is 195.313. Did them all rounding microvolts. So I can get a significantly smaller quantization error by going to more bits and a smaller full-scale range. You do have some control over that. DAC architectures. So these are the different DAC architectures we're going to talk about. Some of these you may have seen in 286. They changed it. I'm sorry you haven't seen them before, but you get to see them now. We'll talk about the resistor string DAC. It's the easiest one to get to. We're going to get to the binary switch array. I think this is where I cut it off, and we'll talk about the rest of these on Thursday. And then we'll look at some ADC architectures and non-idealities. Yes, this really will take me 3 days, I just realized. So the analog world is the physical world, transducers and actuators, all the sensors in your self-driving cars and your self-driving ships. They actually have those now. They've got like the crew down on the ship to like 3 people so people can work in shifts. And all they're doing is monitoring these bazillion sensors on the ship. They're also monitoring remotely, but if something goes wrong, they can do like mechanical repairs and things like that.
You know, like cargo ships?
Yeah, with no staff. So they can like go into the Suez Canal and okay. But they've actually gotten much further with self-driving ships than they have with self-driving cars because there's less things to bump into. And there's not small children running around in the middle of the ocean. But anyways, okay, so we're going to convert from the analog world to the digital world using ADCs. We convert from our computing systems back into the real world using DACs. So these DACs, and this is a review of what we just did, and I have time to get in because it's a slightly longer class. This is a resistor string DAC. Now what I'm going to do is I take my bits coming in, are B1, B2, and B3. And I build a simple 3 to 8 decoder. So if 111 is true, I'm going to call only output A is going to be high. And if 000 is true, only output H is going to be high. And I'm going to do some wiring here and connect by naming convention. I'm going to tie A here, and I'm going to tie H here. So if I'm expecting, if I want to program a 000, I turn this transistor on. Only the one that is, only the 0001 will get turned on, and I'm going to feed roughly 0 volts into this. Now this is a unity gain buffer. One thing you learned in 490 in the fall is always buffer. What this does is it's like a current amplifier. So this can't supply a lot of current, and this is supplying the output, so we want to buffer it so we can actually drive some current. So this has a voltage gain of 1 and a current gain of a large number. And that's what that does. It buffers it. It also buffers not only the resistance, but the capacitance of this device. V out and V plus equal each other because this has a gain of 1 by the rules of op amps, and we won't go into those right now. And the op amps is a buffer. Basically, this voltage has to equal this voltage, and this voltage is tied to the output. So yeah, it's got to be 1. Okay, if I put a 111 in here, I turn this transistor on and only this transistor on, and suddenly the voltage here becomes V out. So whichever transistor is going to control is going to control where in this resistor string my output gets taken from. And this is just a big voltage divider. It's a buffered voltage divider. Ideally, you want this R8 to be 0, but it's not, because you always have some resistance to ground. So there is a little bit of resistance there. And you'd want each one of these resistors to have an equal value. So this one, if you did the voltage divider, it would be R7 over the sum of 8 resistors that all have the same value as R7. So you would get 1/8. So that's how that one works. Problems with this is, especially, you can never match resistors that perfectly. So you're going to get some differential nonlinearity just from the resistor sizes being different. But it's fairly easy to build, except if you want to do it inside an integrated circuit. Then you have the resistor problem. Okay. If you want to build it on a board, you can do that like in 286. How many resistors am I going to need here? Well, this is a 3-bit DAC, and we said this one doesn't count. We're going to need 2 to the n resistors. So in this case, I have 8 resistors, so for 2 to the 3, which is 8. I'm going to need the same number of pass transistors, because I need 1 pass transistor for every single bit. So I need 2 to the n pass transistors. I only need 1 op-amp. And the decoder is going to be n to 2 to the n. So you can see if I went to something like a 12-bit DAC that has 4096 states, I can do that now. Okay, without counting on my fingers. Okay, as 4096 states, I'm going to have 4096 pass transistors, 4096 perfectly matched resistors, 1 op-amp, and a 12 to 4096 decoder. So the size goes up exponentially as I get more bits. Yes?
Does it matter what kind of transistor we use, MOSFETs,
Yes, you could use any kind of transistor if you want. If it's inside a integrated circuit, it'd be a MOSFET. As long as it has a high off resistance and a low on resistance. Now, one of the issues here, particularly with MOSFETs as they're drawn, is that this node right here is the source, or it's the, which side's the higher voltage? This is the drain, this is the source. Well, it doesn't really matter. The gate to source capacitance of each one of those transistors is hanging off that node. And if I have 4096 MOSFETs hanging off of one node, there's my high capacitance node right there. So this has to be, that op-amp has to be good enough to work with that level of capacitance. Is it guaranteed monotonic? Did I explain what monotonic was other than using the word correctly? No, okay, good. Monotonic means if I put a bigger number into here, will the voltage out always be bigger? So a non-monotonic DAC would be something like I put in a 3 and I get 1 volt out. And I put in a 4 and I get 0.75 volts out. This wreaks havoc on any kind of control system. It's really bad. So I cannot, but no matter what, this voltage here is going to be less than this voltage here, no matter how bad it is. This voltage is always going to be higher than the previous voltage. So, yes?
Is there any reason you wouldn't want that monotonic system?
You always want a monotonic system. There are some DACs that are not guaranteed monotonic. And you have to read the data sheet carefully. It's something to look for. Sometimes it's not much of a problem. Sometimes most of the time it is. I haven't seen one sold in a really long time that has said it was not monotonic. It said it, yeah, or did not say monotonic like in somewhere on the first page of the sheet. But there's no telling what's inside your Arduino. I'm serious, these things do not have data sheets on them that make any sense to an analog person. They don't specify the output resistance. And you're looking at the data that you have, and you know it's lousy, but you can't prove to the digital guy who's trying to run this is what it is. And I just say, well, it's not spec, so it's got to be horrible. Just buffer it. It solves all the problems of the world. Just buffer it. We know it's bad. You have to buffer it. Okay, so that's the resistor string. The advantage, it's a really simple design. It's fast as the electrons can flow through here, and you can turn these, and you can decode a state. So one, basically that's going to be one gate delay through here, one transistor delay, and whatever delay you have through the op-amp. So it's an extremely fast design. Resistors have to have the same value, easier to match, but it's hard to do that inside an 80, inside a IC. It's guaranteed monotonic. The biggest problems are I need a huge number of resistors, I need a big decoder, and the DC power dissipation. I've got a resistor string between VDD and ground. It's going to burn power all the time. And you can't shut that down unless you switch the power supply on and off. Okay. DAC topology number 2. This is called a binary switch array. Now what I'm going to do is I'm going to look at my most significant bit is B1. If B1 is true, I'm going to close this switch and leave this one open. And that means that my output has got to come off of somewhere in the upper half of the array. Then B2, the next bit. I set the value of B2. B2 is 1. So I close this switch, and I close this switch, and I leave the rest of them open. B3, let's say B3 is 0. Then I turn on the B3 not switches, and I leave the others where they're at. And the only path I have from this node is through right here. So you use the inputs and the not of the inputs to choose which one of these paths is on. And of course, these switches are transistors.
How is this better?
It is better. How is this better? It's more complicated. You don't need the decoder.
Okay.
Instead of a decoder, you can replace this thing right here, which is getting to be, could be getting to be significantly bigger, with 12 inverters. Okay. Right. Is it guaranteed monotonic? Yes, for the same reasons that the last one was. What does the control logic do? It is a big inverter. It is a 12 inverter. It's 2 to the, it's N inverters, and maybe buffers also. You always need to buffer things. Okay. So, and of course she had to do that. I'll come up with some big formula for that. So the sum of I equals 1 to n, let's say n is 2. So this would be 2, would be, well, I equals 1. 1 minus 1 is 0, is 2 to the 0th, plus 2 to the 1st. That's 3. If I made this a 3, Then I'd have 2 to the 0th plus 2 to the 1st plus 2 squared, which is 7. Okay, why the heck did I do that? That's the number of switches you're going to have associated with this. So for n equals 2, I'd have 6 switches. In this case, n equals 3. How many switches do we have? We can actually count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14. I have 2 times this. Oh, I froze. 2 times that is the number of switches that you're going to have. So for 3 bits, you get 14 switches. For 4 bits, you get 30 switches. For, in general, you get 2 to the n minus 1 switches is how many you need. I will be back in a moment, and we're almost done. Yeah, just kill power.